derived and figuring out which event handler you want to execute. There's the serialization code, which is taking the messages and any structures that they require and being able to format them such that they can be sent on a network communication channel. Then there's the logging that you insert so that you can debug your system. And this can actually sometimes be another 20, 30, or even 50% of the code just in printfs. Then there's the notifications. The pastry layer has to notify the storage layer whenever nodes come and leave so that it can rebalance the data as appropriate. And of course, this is all in addition to the pastry algorithm, which is what we were trying to implement in the first place. So we'd like to avoid doing all this extra tedious work and focus instead on the algorithm. Now the way we do this in Mace is by providing a high-level state machine representation along with an interface definition. So the interface definition is much like any interface, like a Java interface. You specify the set of methods that this service provides. We call them downcalls. And then the high-level state machine representation, which says when I receive a particular event, here is what I'm going to do. You take these two inputs, you pass them to the Mace compiler, which will output three things. First, a high-performance implementation in C++. Second, a set of debugging and testing hooks. And third, an annotated structure of your system. Now we'll take the first of these, the implementation, and link it together with your application, your user interface. And this can immediately be run on the internet. We'll take the annotated structure and pass it along to a set of visualization tools that can take advantage of the structure and show you what it is that your system is doing. The Mace model checker will use all three of these pieces. It will run the unmodified implementation, it will interact with the implementation using the set of debugging and testing hooks, and then it will make sense of what it's doing using the annotated structure. And finally, the pip path verification tool will use the implementation and the structure to understand what it is that's going on. To implement a system using Mace, you essentially fill out this template. So at the top of this template is the architectural information. So this includes all of the layering of your service. You know, the pastry layer is beneath the storage layer and on top of the transport layer. So this is to say that pastry, which is the name of the service, provides the overlay router interface and uses as a lower level service a TCP transport. Then there's a set of generation options, which are flags to the Mace compiler to tell it to turn on and off certain automated logging features or include other files in this implementation, that sort of thing. Then there's a set of type definitions, which among other things include the set of messages that you're going to be using. Now what's important here is that to define a message in Mace, you essentially define a struct. You need not define any extra fields, any constructors, anything like that. This code is very meticulous and monotonous and is roughly the same code every time by substituting variable names and types. So the Mace compiler can automatically generate these implementations for you, and will. Next comes the persistent state that you store. This includes a set of constants, a set of the high-level states that we talked about, a set of constructor parameters, and any other variables that you maintain from one event to the next event. And then finally is the execution portion of your service. This is the transition arcs, how you get from one state to another state. So by filling out this template, you can implement a service using Mace. So this slide is giving us a sampling of some of the systems that we've built using Mace, as well as where they were originally published, a comparison of the lines of code of our implementation to the original implementation by the authors, and finally a speed category. Speed has been normalized such that bigger is better. For different services, it might be latency versus bandwidth. So in some cases, bigger or smaller, but it's been normalized to give you some relative experience here. So these systems span everything from overlay protocols to consensus protocols to file distribution protocols to network location protocols. And as you can see, none of these papers were written by me. So a side effect of having done this research is we've gone out and we've reproduced the research that other researchers have also done in order to provide this sort of missing link in a lot of systems work, which is reproducing other people's results. In each of these cases, our implementation, which is the George Jetson implementation, the blue implementation, is shorter and faster, and certainly no longer. And in terms of speed, for most of the implementations, it's faster. In some cases, it's no slower. So this gives us some confidence that our language, our toolkit, our libraries are high performance, are expressive, and are in fact quite effective. Some of these implementations were also done quite quickly. The Bamboo implementation, for example, we did in a matter of 2 days. That includes building and testing. So we're very happy with this Mace implementation. Are there any questions about the Mace programming language, the toolkit, anything that we've covered so far? Okay. So moving on, we'll now talk about the Mace model checker. So the Mace model checker we'll focus on a particular protocol that we tested using the Mace model checker. And we'll talk about Pastry, which is the same example we were talking about from before. Importantly, Pastry maintains a set of pointers to successor and predecessor nodes. In doing so, it creates this ring. And the ring is critical to the correctness of Pastry. If the ring is correct, then a lookup in the DHT will eventually find the correct node based on the implementation. So this is what Pastry needs to maintain as a correctness property. Of course, it's not always going to be true, because when a node first joins the network, the ring won't exist. Now, Pastry does handle things like node departure. So if node A wishes to depart the network, he goes offline. Nodes B and F are responsible for detecting and recovering from node A's failure by correcting the successor and predecessor relationships. It also handles node arrival. Suppose node A comes back online. It's going to send a join message to a bootstrap peer, which in this case is node D, who will forward the join message to node A's closest peer in the network. That's node F. And that's because node F needs to be node A's predecessor. Node F will then respond to node A saying, I'm your predecessor, and node B is your successor. Finally, node A will tell node B and F that it is online and ready for operation. At this point, it is now rejoined in the network. So the Pastry protocol handles node departure and arrival, at least most of the time. We found as we were testing our implementation that sometimes when node A tries to join the network, it's unable to join the network. Perplexed by this, we went to the logs to try to figure out what was going on. And the only notable thing in the log was this warning message. Warning, I tried to do leaf set maintenance, but the leaf set was empty. Now, without having to understand the details of the protocol, leaf set maintenance is a periodic action that tries to correct the successor and predecessor pointers. And until the node is able to join, it makes sense for the leaf set to be empty, because you have no successor and predecessor. So in this case, this warning, though it does indicate a problem, is not helpful to figure out what the problem was, or why the node was unable to join. So Fred, in his implementation, tries to solve this problem by adding logging, by trying to reproduce it on the internet in a LAN, and he's unable to track down the problem using these tools. George says, hey, I've got an idea. This logging thing isn't going to work out, so we should use model checking. Now, model checking in this context is going to be systematic state space exploration. On the left-hand side of the slide, we're showing the state of the system. That includes the state of the two nodes, as well as the state of the network. And on the right-hand side, we're showing the portion of the state space that we have explored thus far. So we start from the initial state, which is we've just booted the two nodes, and there are no messages in the network. We can either initialize node 1, or we can initialize node 2. These are the only two things that can happen on an execution of length 1. And doing so, we have explored the entire state space of length 1. We'll now proceed to explore the state space of all executions of length 2. After initializing node 1, you could reset node 1. It could reboot. You could initialize node 2, or node 2 could receive a message that was sent by node 1 in node 1's initialization step. There's a similar set of options had you initialized node 2 first. And having done this, we've now explored all possible executions of length 2. Now, of course, you can see that as the execution length grows, the state space will expand exponentially. So we will not be able to systematically explore the entire state space of a system like Pastry, because the state space is far too large to do systematic state space exploration. So instead, we want to think about this problem. What is it that we're doing? We're trying to produce symptoms. That is to say, we have an implementation of Pastry, and we have a symptom. The node cannot rejoin. We'd like to pass these two things to the model checker and have it output an execution that exhibits the symptom. So with existing model checkers that can test systems code, unmodified implementations, they can only test safety properties. So a safety property is, roughly speaking, a set of executions satisfying always P, where P is a state predicate. So for example, an assertion is an example of a safety property. Whenever the program counter reaches the line of the assertion, the property must be true, otherwise you've experienced a bug. So let's try having our symptom be a safety property. Right? If the nodes always form a ring, this will not be a safety property. The model checker will return instantly, because right after booting all 6 nodes, they will not be in a ring. A safety property is something that must always be true. So this cannot be a safety property. All right? So maybe it's the case that if I have a successor, the successor's predecessor should be me. Seems like a sensible safety property, except that in a distributed system,